Hey there, we're going to go over some notes to kind of introduce us to forces. And so, a force, you probably learned about a little bit of this in middle school. And the basic definition is that it is a push or pull on an object. So, that's just the basic definition of a force. And a force is measured in what we call newtons. That's our unit of measurement. And we use a capital N for newtons. So time, we use seconds. Force, we use newtons. And 1 Newton is equal to 1 kilogram times meters per second squared. But it's more convenient to say I have a force of 5 newtons than I have a force of 5 kilograms times meters per second squared. So that's the unit that we use for force. You'll kind of see where this comes from once we start looking at the actual equation in calculating a force. And there's different types of forces that we're going to work with this year. We'll talk about some of the common ones. First one is tension. In tension, we just use a T, a capital T for tension. Some people like to put F subscript T. It's up to you. I prefer just a capital T. In tension, that is whenever we have some kind of a string or a rope. So if something gets connected to a string or a rope, then there's some tension there. Another common one that we're going to see is what we call the normal force. In the normal force, we use the symbol F subscript N. And the normal force, this is a contact force. So anytime an object is in contact with some kind of surface, there's going to be a normal force there. And the thing about the normal force is that it is always perpendicular to the surface. Okay, we'll look at some examples of that when we draw some free body diagrams. Another one we have that's common is friction. And for friction, we just put F subscript F. And then friction, that there's a misconception. When you ask somebody what is friction, they'll say it opposes motion, but that's not the case. Most of the time, yes, it will oppose motion, but sometimes friction is what helps us propel forward. Okay, so sometimes it helps us propel forward. And we'll look through some examples of this a little later. We also have a push force or applied force. So push or applied. And usually we put a F subscript P. And so this is anytime you're pushing or pulling on an object. So if I'm pushing a box down the hallway, then that's a push force or applied force. And another common one is this force of gravity or gravitational force. And we use a F subscript G. So this Fg, this force, gravitational force, this is basically the weight of an object. Now you're probably used to weight being in pounds. So if I said how much do you weigh, you'd tell me how many pounds you weigh. But in physics, for the weight of an object, we use newtons. Okay, there's actually an equation specifically for this gravitational force. And that equation is F subscript G is equal to mg. And the m here is the mass of the object. That needs to be in kilograms. And then the g here is just your gravitational field, right? And on the surface of Earth, it's 9.8 meters per second squared or newtons per kilogram, but for our class, we just round that to 10 newtons per kilogram or meters per second squared. So we can calculate the weight of an object if we know the mass in kilograms. Okay, for example, if I said I had a 5 kilogram object and I want to know the weight or the gravitational force. So to do that, we would just plug it into this equation. It'd be 5 kilograms times 10 newtons per kilogram. My kilograms would cancel. So the weight of this object would equal 50 newtons. We can also work backwards and solve for the mass of an object if we know the weight. Okay, so using this same example, if I said that I know the Fg is equal to 50 newtons, what's the mass equal to? My equation is Fg equals mg. Rearranging for m, it would equal Fg over g. So then that would give me 50 newtons divided by 10 kilograms, which equals 5 newtons per kilogram. So this force here, this gravitational force, has a specific equation that goes with it. Okay, normal force, frictional force. There is an equation for frictional force. We'll get into that a little later. Push force. We solved those two just using our free body diagrams and net force equations, which you'll see here in just a little bit. So what we do is, and once we are looking at a situation, we end up making what we call free body diagrams. Sometimes you might see that FBD, okay, free body diagram. There's some people also call these force diagrams or free body diagrams. Well, what that is, a free body diagram, it shows me a visual representation of all the forces on an object. So usually the steps here is you're going to be given some kind of a problem, and the first step you want to do is make one of these free body diagrams, these visual representations, before you just start solving the problem. And we'll look at a couple of examples on how we draw these free body diagrams. So let's say for example, I have a water bottle that's just sitting on the desk. And I said I want to draw a free body diagram of that water bottle. Now, we mentioned in the last video, right, we don't have to actually draw the water bottle for the object. Instead, we'll just draw a box. Okay, so here's my water bottle. And it's sitting there on a table. Okay, it's at rest. Okay, so we know it's at rest. And if you remember, we said if an object is at rest, it has balanced forces. So if you ever see the word at rest, you usually want to underline that word. That's an important word. So our water bottle, it's in a gravitational field, right? It's here on the surface of Earth. Any object here on Earth has this gravitational force. And the gravitational force always goes straight down. Okay, it never goes at an angle, it always goes straight down. So you're going to draw an arrow going straight down. But you always want to label your arrow, okay, with the type of force. So this one is a gravitational force, so I'll put an F subscript G. Now we said it's supposed to be balanced, and looking at that picture, you should recognize that is not balanced. Well, there's another force that is involved that is balancing out this gravitational force. In order to balance it, that means it has to go straight up. And the water bottle is on a surface, right? And if you remember back from those forces that we kind of talked about, that contact force on a surface, that was that normal force. So we have the normal force, so F subscript N. And now we're all done with our free body diagram. One thing that you need to note here when you draw these free body diagrams, the length of your arrow is important. Okay, so the length of the arrow represents the magnitude or the size of the force. So if I drew this one with my FG down, and then I drew my normal force up, that is not balanced. Okay, so that would indicate that the normal force is greater than the gravitational force. So it would not remain at rest. So the length of your arrows is important whenever you're drawing them. Let's look at a couple more examples drawing these free body diagrams. Let's say that I have a sign that's hanging by a string from the ceiling. There's my object, there's my sign, and it's in this gravitational field, so we know we have Fg going down. We also know that it's just hanging there, so it's at rest, which means it needs to be balanced. Okay, and so the string that's pulling up on it has to be the same length as my gravitational force. And remember, a string is just a tension force. So we could put a T up there, and now we're all done. Let's look at another example. Let's say now it has two strings. So we'll draw our box, and now we have a string here and a string here. And we want to make a free body diagram. So I would first draw, so there's the sign there. Let's draw the free body diagram. We'd have Fg going down. And now I have two tension force. But remember, the length, the magnitude has to balance out because it's at rest. So what that means is this tension force here, I'll call this T1, and this tension force here, if I add those up, they have to be the same length as this one gravitational force. Okay, so this one plus this one has to be the same length as this one here. Because again, it's at rest, so they're balanced. Okay, so the two tensions are working together, they're pointed in the same direction, they have to equal the same magnitude as the Fg pointing down. Here's another example. Let's say I'm pushing a box down the hallway at a constant velocity. Okay, so here I am. I'm going to push this box down the hallway at a constant velocity. Now the key word here is constant velocity. So if you see at rest, you want to underline that. If you see constant velocity, you want to underline it. Because both of those situations, if you remember back from the Newton's first law, mean that we have balanced forces. So let's draw our box. We know that we're in a gravitational field, so you're always going to have Fg going straight down. Should be balanced. Okay, it's on the floor, so I'm going to have that normal force. And I'm pushing it down the hallway. So I have this push force here, or applied force. Looking at that though, that's not balanced, and it's supposed to be balanced because it's constant velocity. So there's some kind of force that is going this direction that has to be the same length as that push force. And that force would be friction. So anytime an object is sliding across a surface, if the problem does not say frictionless, that means there is friction present. All right, so that's how we make the free body diagrams. The next step in solving a problem dealing with forces is to make a net force equation. And when we make a when we make a net force equation, we have to keep our y direction separate from our x direction. So what we end up doing is we make a net force equation. So there's the symbol net force in the x direction, and we make a net force in the y direction. And so we're going to build our equations based on the situation. So if we're looking at this example right here with me pushing a box, if I want to make a net force equation in the x direction, we're going to look at all the forces that are in that horizontal x direction. Now, generally what you do is you call right positive, left negative, you call up positive, down negative. But you can actually call left positive if it makes the situation a little easier for you. Okay, so you're able to call whichever one you want, positive and negative, but generally speaking, we usually do right positive, up positive. So knowing that, looking at that diagram, in the x direction, the force that's in the positive direction, I'll write that one first, that's a push force, so FP. And then the force that's pointed in the negative direction is my friction. And we know that it's moving at a constant velocity, so that net force equation has to equal to 0. So there's my first net force equation. In the y direction, in the positive direction, we have that normal force, so I put F in. And then in the negative direction, I have Fg. And again, it's balanced, so it's just going to equal 0. So far what we got in solving a forces problem, the general steps here is you're going to be given some kind of a problem, a word problem. You want to first make your free body diagram, and then from there you can build your net force equations depending on that situation. Once you do that, then you can just solve for any unknown force. So we'll look at one example together. Let's say I have this object here, and it's sitting on the floor, and it has a mass of 10 kilograms. And I want to solve for the normal force. Let's say that we're pushing this object with the 800 Newton force. So that push force is equal to 800 newtons. Let's say that the friction is equal to 500 newtons. And let's say there's some other unknown force here. And I want to solve for that unknown force. So I'm solving for two things here. Now, in drawing our free body diagram, we need to also draw those in the y direction, and we know there's always going to be an FG straight down. And we also know that there's going to be a normal force the same size going up. All right, so let's start out with solving for the mass of that object. Okay, so we know the mass is 10 kilograms. Now, if you remember from earlier, we said that your Fg is just equal to mg. And in this case, the mass is 10 kilograms. You're going to multiply that by 10 newtons per kilogram. Kilograms will cancel. So the weight is equal to 100 newtons. And if I make my net force equations, in the x direction, in the positive direction, we have Fn. Oops, that's the y direction. So let's start with the y. So in the y direction, we have normal force minus the weight, and that has to equal 0. The problem wanted me to solve for this normal force. And because this is equal to 0, we know that the normal force is just equal to the weight, which is equal to 100 newtons. So my normal force is equal to 100 newtons. So there's the first one we're solving for. Now we need to solve for that unknown force in the x direction. So let's make our net force equation in that x direction. So your net force equation in the x direction is going to equal that push force minus the friction, because that's in the opposite direction, minus this unknown force. Now we subtract both of those because those two are pointed in the same direction. So that means they both have to be negative here. And we also know that equals 0. So if we rearrange this equation, okay, we're solving for that unknown force, so we can add F to both sides. And if I do that, then that means that this unknown force is going to equal your push force minus the friction. And the push force we said was 800 newtons minus your friction, which is equal to 500 newtons. So this unknown force then is equal to 300 newtons. And you can check yourself to make sure you solved it right, because this is a constant velocity, so the forces have to be balanced. And if I add 300 here, 300 newtons, that's 800 to the left and 800 to the right, so we know we're good. Now, one last thing that I want to mention here is with that normal force. We said it's always perpendicular to the surface. So let's look at a situation where it's not. So if I have an inclined ramp here, and a box is sitting on this inclined ramp, and let's say it's just sliding down this ramp, and we'll call it a frictionless ramp. Now I want to make a free body diagram. So if I draw my box, I'll kind of draw it at an angle here. Now FG, we know it always goes straight down. So FG will still be down. The normal force always has to be perpendicular to the surface. Okay, so it's always perpendicular to the surface. So how I would draw my normal force here then, I would draw it this way, because it has to stay perpendicular. Okay, so keep that in mind when you're drawing these free body diagrams, that your FG always goes straight down, normal force is always perpendicular to the surface. So just to kind of sum everything up, when we're working with these force problems, okay, the first step, what you want to do is make this free body diagram. Okay, once you make a free body diagram, then you can kind of picture everything. You can build your net force equations. And once you have your net force equations, then you can solve for these unknown forces.